Okay, so thank you very much for inviting me. I'm sorry that I'm not in Philadelphia, but it's still nice to be kind of broadcast essentially from Stuttgart University. So the title of my talk will be Bio-inspired multifunctional polymer films for actuating devices. I'm part of this soft material robotics priority program, which was introduced by Professor Rath. And it's a great pleasure to give a bit the material science point of view. And I really love the talk of Professor Sutsumori as an opening talk from the soft robotics side, and he put his expectation. So he put a high expectation level for a material scientist such as I am. To be more precise, I'm coming from polymer chemistry actually, but we love to do polymer materials. So my bio inspiration comes actually from visits of the botanical garden, which is headed by my colleague Thomas Speck at Freiburg University, which is not too far from Stuttgart, where they're studying rhododendron flowers. So the leaves of rhododendron, which are essentially just layered architectures, which are built due to self-assembly. So you have this epidermis, two mesophyll layers, and a lower epidermis. And this layered multifunctional structure is quite clever because these leaves look completely different on a mild spring day as it is today in Stuttgart compared to a cold winter day. Another example from the Speck group is for Aramunda mycone. So there's pretty flowers here. What they did is they cut off the leaves of this pretty flower. And then they took successive videos during dehydration and during hydration again. So that's happening during dehydration. So you really see that this leaf is kind of changing completely its shape. It's also changing completely its mechanical properties. And this can be kind of gained back when they rehydrate it. So when I put it back into water, so when they submerge it. So that's really amazing, I found. And that works as a very nice bio-inspiration for material scientists, because we are able to build multifunctional and also hierarchical architectures, for example, using the principles of self-assembly, which were mentioned in the opening talk as well. So when one thinks of polymers, one usually thinks of plastics, and there are these commodity polymers like polystyrene or polyethylene. A lot of research in the soft robotics area is also based on these PDMS compounds. I learned from my colleagues in Hanover that you use also EcoFlex or dragon skin and how they are called, but they are flexible elastomer cross-linked polymers essentially. What we are more interested in is going towards functional properties, so putting additional functional moieties on them. And one example is this polystyrene sulfonic acid. So here you see the sulfonic acid. This is the class of polyelectrolytes. They call, if you use polyacrylic acid, which is kind of another polymer from this class, you can, for example, make these baby pampers, or also these pretty pearls, which you can buy and which swell up in contact with water. By the way, the sulfonic acid bearing polymers are also in these polyelectrolyte membranes, which are used for fuel cells and which were mentioned as well in the talk before. So coming from this ion conducting polymers, as they are as well, or as they can be termed as well, I'm much more interested in further going, and this is a class of conducting polymers. Conducting polymers, just briefly to their chemistry, that's a polythiophene backbone. So the main principle of a conducting polymer is that you have double and single bonds which are alternating, and you can use these so-called conjugated systems in a kind of doping way, where you take out electrons from this backbone and you put charges on this polymer backbone. And that can be reversibly done, so that you can change between the neutral form and the doped form of this polymer reversibly. You just have to add additional ions to the systems, which then work as counter ions to overall fulfill the rule of counterbalancing charges, of charge neutrality, essentially. This counterbalancing of the charges works, for example, when you do the doping in a so-called electrochemical experiments, where you have films of your polymers on so-called working electrodes, and then you put everything into an electrolyte, and then ions can move out of the electrolyte into the polymer. So this is a nice field of research, and the good thing about these polymers is, or in general, of polymers is that they are lightweight, they are solution processable. You can tune their morphology, as is shown here, for example, with this AFM phase image, and they allow also low voltage operation. One of the tasks of my group, or one of the highlights of my group, was, for example, that we could tune the conductivity of such polymers by changing the doping potentials during electrochemical experiments. And what you see here, when you look at the conductivity on the Y scale, this polymer is kind of neutral at normal conditions, and then it would be kind of in this form. When you dope it, then you reach here 200, around 200 Siemens per centimeter, which is already good. There are also systems which go to 2000 and more Siemens per centimeter, then reaching the capabilities of synthetic metals. Remember, for the talk, this is kind of the doped form. So when they are in the doped form with the counter ions, then they can conduct. A very interesting material, which is additionally also commercial, which makes some of the applications easier, is this so-called P.PSS. So if you look again on the top structure, on the red one, that's very similar to the chemical structure I've just shown before. So that's also a polythiophene in its doped form, so in its highly doped form, together with a polystyrene sulfonate, also this chemical structure I've shown before, that's a polyelectrolyte. So this combination, that's a blend, you can buy as aqueous dispersion. And then if you deposit that on a surface, so if you make films of that, it self-assembles into domains which contain the electronic conducting polymer and the ionic conducting polymers. And this P.PSS polymer has found a number of different applications. So it's one of the workhorses of the flexible electronics community. So for solar cells, displaced transistors. So P.PSS is heavily used in that. We were more interested in kind of their genuine properties. So on the one hand, it is this electronic conducting polymer, so it can be electrochemically triggered and changed in terms of doping state. And on the other hand, it is also humidity responsive, because this is the polyelectrolyte, which gets ionically conducting as function of humidity. Okay, let me start. So what has been long known essentially is electrochromism of P. So if you have the doped form here in blue, in black, and here is a non-doped form, that's a neutral form in blue, the films look differently. So the doped form looks transparent. So this is why it's also used as a transparent electrode for flexible electronics, for example. The neutral state appears blue. If you do that scientifically more in depth with absorption spectroscopy, then you see this is absorption as a function of wavelengths. In black is the doped material. So here the absorption and the NIR. When you de-dope the material, then you have an intermediate state which has the red absorption curve, and in the neutral state it shows this blue absorption curve, which I highlight here also with the potential. So minus 1.57 volt means that the polymer is completely in its undoped form, in its neutral form, whereas at plus 1.04 volt, it's fully doped. And we can switch between these two states. Coming from classical electrochromism, we are preparing currently a paper actually with my colleague from MIT, Matthias Kolle, where we use bilayers of P.PSS and PDMS. So PDMS was this elastomeric material, very thin layers. They are just a few tenths of nanometers thick, and we roll them up on carbon nanotube fibers. And what we see is that these fibers have a certain color. So my colleague Matthias Kolle is specialized on the optics. And what we see is that this material, so this multi-layer cladding, so this photonic fiber appears red in the doped state, and it appears kind of blue, and you can't see the color here anymore, at minus 1.52 volts. So if it's fully de-doped, then the color changes. So this is what we attribute to the absorption color of the neutral state, whereas the state at plus 1.08 volt is actually attributed to a so-called structural color because of this particular building up of the fiber, this multi-layer cladding. So there are interference effects in the game, essentially. Here you see it nicer for the picture. So the reflectance is really changing here from red to going down here in this direction. And also here you can reversibly change this reflectance in an electrochemical experiment. So that's one nice property using this electrochromism and going towards structural colors, where you can change the structural colors also by changing the film thickness. The other example is actually based on, and that is a similar graph you have seen before. This is conductivity as function of the potential in an electrochemical experiment. So we know that at certain potentials, we are in the doped state. So that's also a kind of plateau conductivity. And at low potentials, we come to the neutral state. So when there's no real conductivity measurable. So here we can also talk about a metal state, metal-like state in the doped state, and a neutral non-conducting insulating state at low potentials. And this is what we are making use of together with my colleague, Professor Giesen, who is an optics photonics expert who managed to structure this P.PSS in little nano antennas, sub-wavelength nano antennas, and then putting the whole thing also in an electrochemical setup and going with an IR laser and then looking at the transmitted intensity, we can produce actually nano antennas, which we can switch off when the P.PSS is insulating and switch on when the P.PSS is metallic. And this metal insulator reversible switching of the material properties of the plasmonic resonances essentially works at very high frequencies here at 30 Hertz. And this is due because these are really small feature sizes. So look at the length scale here. What one also learns when looking further in the P.PSS material is, and the method of choice we took there is spectroscopic ellipsometry. We saw that when we make films on the surface and we switch essentially the electrochemical doping potential between the doped and the neutral state, we also see film thickness changes. So you see the doped state here during an electrochemical experiment amounts to roughly 140 nanometer. In the neutral state, the film increases to 230 nanometer. And this can be explained actually that during this doping and de-doping procedures, ions have to be included for charge neutralization, as I said before. And together with the ion, there's also usually solvent getting included in the system as well. And that leads to overall swelling. So there is a lot of changes in film thickness and in degrees of swelling. And that's as motivation that this can be used for actuator design. I'm not going to talk about this electrochemically induced doping in this talk, but I want to switch to an easier stimulus, and that's the stimulus of humidity. And for that, I'm just using essentially the PSS compound in the P.PSS, because you remember I said that's a polyelectrolyte. We have self-made chambers where we create relative humidities between 0 and 90%, that's 25 degrees. So we can tune the relative humidity, what that means we can tune the environmental conditions reliably. And we do that by mixing nitrogen streams here, a pure nitrogen stream, which goes through line A, and a nitrogen stream, which bubbles through water and makes a saturated water atmosphere. And then by mixing these two streams, we can define actually the vapor pressure in self-made chambers, which then relates actually to the relative humidity. And taking now these P.PSS films, and using the so-called method of quartz crystal microbalance, QCM, And by using in these regimes is possible the Sauer-Brei equation, where we get frequencies out and related to the mass, we can actually calculate the water content in the film. So when we take such a P.PSS film, as I said, it's this kind of self-assembled morphology. The blue phase is the polyelectrolyte phase, and this material takes up water, and you see here that's a dry state at 0% relative humidity, and that would be 90% relative humidity. So we have here 50% water uptake actually in the film. So the film is increasing also in film thickness, but it takes up the water. So we can reliably determine the water uptake. We have also used AC impedance and DC measurements to decouple electronic and ionic conductivity. The ionic conductivity becomes prominent actually when we are especially at high relative humidities, because then the ions can nicely get kind of transported through the blue phases in such a co-continuous morphology. Coming from that, we wanted to build actuators, since we know that the P.PSS can take up the water, so it changes, it swells in water. So we thought of the easiest possible geometry, and that's a bilayer. So we combined P.PSS layers. In this case, they are thicker. So this is kind of P.PSS about 5 micrometer, and the PDMS is bigger with 50 micrometers. So we made it on PDMS, which is essentially a passive layer, and P.PSS, it's an active layer which can react to the relative humidity. And that's one of these experiments, and you see it looks very similar to the leaf of the botanic garden. So this actuator, this simple bilayer actuator, can actually change its shape from being elongated and then being curled. So it really curls in here. And together with my colleague, Professor Steb, who is also my collaboration partner in this soft material robotics project of the SPP, we wanted to understand this phenomenon even further. So we built these actuators. In a first step, we just did fitting of the curvatures, which you see here. This is the curvature as function of the relative humidity. Again, here from dry conditions to 90% wet conditions. We find reversible kinematics, and we don't observe any observable hysteresis, which is already good. And one step going further, so in this particular experiment, the passive layer was 10 micron, P.PSS, as I said, 5 micrometer. So the idea was really we use defined rheology as function of the relative humidity. So we make these films, which we use for the actuators, also for rheological measurements. And from the rheology experiments, which are based on tensile tests and also DMTA measurements, we get out the elastic moduli, but also volumetric strains. We put this then into a model. As you will see, that's a model of Timoshenko. And we can actually, with the model, by using the parameters from rheology, we can kind of predict the bending behavior, and we can compare that with the real actuation images, actually, which we take during the experiment of the actuators in wet atmosphere. So this simple analytical model is here based on a composite beam theory, which is coming from Timoshenko. Just quickly going through the equation. This is the curvature, epsilon volume is the volumetric strain. D is the film thickness of both layers, so the film thickness of the P.PSS and the film thickness of the PDMS. And what else is in there? There's the elastic modulus, the Young's modulus of P.PSS and the Young's modulus of PDMS. Remember, PDMS is quite soft, and the Young's modulus of P.PSS changes actually as function of the relative humidity, as you will see in a second. And here, this M parameter is here the thickness ratio between the P.PSS and the PDMS. So these are the results. Look at the bottom graph first. This is again the picture I've shown before. That's the increase of water uptake with increasing relative humidity. And concomitantly, you find here the storage modulus as function of the relative humidity. And what we see is that this decreases with increasing relative humidity here by a factor of 2.4 between the dry and the wet state. So this is definitely a function of the relative humidity. And if we put all these parameters, which we experimentally determine in the Timoshenko equation, then we can do these predictions. And one example of such a prediction for these bilayers is, this is curvature as function of the relative humidity with a thickness of 17 micrometer of the whole bilayer. And here, the graphs here in black, red, and blue are just shown for different input parameters of the Young's modulus for P.PSS. So let's take the completely dry one that's at relative humidity 1%. So this shows this kind of curvature, which is not so realistic. Actually, it gets more realistic when we take the values either of the elastic moduli taken at 30%, so at humid, at ambient humid conditions, or if we use the values which are varying on the relative humidity, as you see with the black points here, then it's even giving more realistic values, and then we get also higher curvatures. And that's kind of for a 5 millimeter actuator, the prediction how the rolling up of the actuator would work, of the bilayer would work. With that, I'm coming to the end. So that's just based on simple bilayers. We are interested in more complex geometries, also based on self-assembly and smart material choice to at some point be able to really mimic biology, such as these leaves. With that, I'm fully at the end. Many thanks to the people who did the work. This is mainly work from Carsten Dingler's PhD thesis and David Neusser's PhD thesis. And I thank my collaborators from Stuttgart, from mechanics and from physics. So this is essentially an interdisciplinary field. So these questions can only be done together. And I'm looking for exciting discussions about the use in soft robotics further. Thanks a lot for your attention.
Yeah, just one quick question out of curiosity. You said that this one material is commercially available. Do you have a price for that material? Just, you know, I'm interested into that.
Okay, I think we checked it out. I think 25 gram was kind of 200 euro or something. Oh, okay. So yeah, but we can, I mean, we are still planning our collaboration. So you should come to Stuttgart and we show you the material. I mean, it's a water, yeah. It's an aqueous dispersion, yeah, but you can also buy them in kilogram.
Oh, okay. That's good to know already. That's normally what we use as kilogram dimensions.
Yeah, that's exactly something which is at this interface between material science and application-driven research.
Yeah, application-driven research.
Where you need a lot of material, yeah.
And another quick question. I was very impressed by these color changing abilities of your materials. Is there an application for that? I mean, is there some kind of gecko robot you can imagine, or?
Yeah, my colleague Harald Giesen, who makes these plasmonic nanostructures, they want to go to holographic imaging essentially. So one application is really that you get a hologram of someone, and that could be included in the soft robotics. So as a smart tool, so that the human robot interaction could work or could be improved essentially, possibly.
Okay, so it sounds like a very interesting future application, I would say.
Thank you very much, Sabine, for sharing these insights. I was wondering if you can share some or elaborate more on how to manufacture these bilayer P.PSS, PDMS actuators, and also maybe comment on the dynamic behavior of these.
Okay, thank you very much for this question. I mean, our typical processing technologies is spin coating or blade coating. Yeah, so these are thin layers. So these are layered architectures. We're currently also going toward more hydrogel architectures, macroscopic samples. which will make our life easier as well for the rheological measurements. Yeah, because it was a kind of tricky situation to get these very thin layers and then to spin them into a DMTA measurement and then do this rotation and oscillation experiment. That was kind of tricky. So we are now going to increase kind of the bulk of the materials as well. But in principle, this is from water dispersion, so you can process them over large areas. And this is why they are so much used in flexible electronics as well, because they talk about roll-to-roll casting, for example. Newspapers are kind of printing technologies. Does this answer your question?
Yes, thank you. And the dynamic behavior, maybe you can.
Yeah, so the dynamic behavior, we of course on the one hand look at with the rheology, and on the other hand with the with simple optical microscopy or cameras even. These things are not optimized for fast switching at the moment, yeah, and that's a problem of the humidity as well. So we're currently looking into materials which change their shape more vertically. So there are polymers which react to which are called thermosensitive materials, which would even faster react to the stimulus. And this is why I'm going currently also towards the electrical stimuli more, because they go on a switch. Yeah, humidity is something autonomous, but usually slow. Yeah, I mean, we have to admit it. It depends on if you make a thick layer, then you can imagine the water uptake and the water going out takes a long while. So you want to have something which on switch kind of changes its shape.
Yeah, everyone saw the bending behavior. Is that also elongation then? And how is then the material properties changing if you stretch it, for instance?
Yeah, thanks for this question as well. So this was just hold at one end, and then we looked at it. In the rheology, it's kind of hold under stress, essentially. So it's kind of kept straight. In principle, you can change the properties of the P.PSS further by kind of mixing them with elastomers as well. And then you get more in this stretching behavior. So you get more what you want for the soft robotics, which is always over strains over 100%. But for that, you have to convince the P.PSS to be more stretchable as well. So there are some tricks to be played from the material science point of view again.
Thank you.
Last question.
Yeah, thank you for this very interesting talk. I was wondering, I'm coming from the stretchable electronics community. So did you do some long time tests or some, fatiguing of these materials?
No, we didn't. No, we didn't. We are not that far yet. So we were happy that it's doing something. And and the point was really that we wanted to understand it. Yeah, so we want to use. We believe that by knowing the material properties, we can actually do all of the predictions. So that was more towards this predictive behavior and the loop in the material properties, because by the predictions we can say, okay, this layer has to be thinner or thicker, or we have to change the E modulus in such a direction. So no real fatigue and no reliability tests. No.
Thank you.
Yes. So can it work as a sensor, some kind of strain sensor or something?
It can also work as a sensor. I mean, that's this game of it acts depending on the relative humidity as outer input, but it can also sense the humidity as an outer input. I mean, you can use it like that as well. As strain, I mean, what Ingrid Gard said as well, as strain sensors, that would be highly interesting. We haven't done that.
Oh, okay.
Yeah,
okay,
this is when we need to talk with the people and also with electrical engineers to kind of put the bits and pieces together. I think that is what this field, why this field is so interesting of soft robotics, because you need the different expertises to solve these issues. Huh?
And can it work as a generator also? Can it harvest some energy?
I mean, you can combine it with solar cells, for example, if you want, and then you can do it as autonomous systems. I mean, that is also what Professor Susumori showed in the first talk as well, that you have the battery and then this kind of drives also the kind of what is a fuel cell-like thing. So you can combine these parts because they have low voltage operation. I mean, I showed the examples of this electrochromism. You could even see if you make such batteries, for example, such moving devices, if they are low of power, they could change their color, for example.
Okay.
So there's
Okay.
lots of possibilities and imagination possible.
Okay, thank you.
Yeah.
Thank you very much for all the questions already. I like this discussion that we have here already. But now I would like to go to the next talk. Now we have Rini Zhao, so one of our co-organizers presenting here in person. So I hope the technique now works on the first try.
Good morning, everyone. Rini Zhao from Stanford University in Mechanical Engineering. And first of all, I would like to thank the organizers for putting together this very exciting workshop. And also, I'm really looking forward to the discussions today with all the speakers and the audience. So today I'm going to talk about our recent work on magnetic self-composites and also magnetic robots, basically the applications for miniaturized biomedical devices. So let me start from a brief introduction of the magnetic self-composites. So for these composites, basically what we do is that we embed hard magnetic particles in different types of soft matrix. And then these particles are actually hard magnets. Basically, it means that it has its polarity after we post-magnetize it. So if now we carry the soft composite and then apply external magnetic field, and then the polarity of the soft composite will try to align itself with the external field, and that gives us the deformation or locomotion. So the reason that is a very promising material for designing biomedical device, especially for drug delivery and minimally invasive operations, there are two major reasons. First of all, the magnetic actuation is a remote actuation method. Basically, it provides a strategy to not cutting human body open, just to apply the remote control and manipulate the object inside of the human body. And secondly, because this is a remote control method, and it can effectively separate the power source and the control unit from the device itself. This is how we use this control technology to make the device really small. So today there are two topics that I'm going to discuss. The first one is a new material that we developed 2 years ago called magnetic sheet memory polymer. And the second one is magnetic origami robots. So starting from the first topic, so for this work, we actually developed a new composite, as I mentioned previously, called the magnetic sheet memory polymer, where we can actively lock and unlock the deformed configuration of the material. In the meantime, we're combining the actuation and stiffness tunability of the composite. So this is a collaboration with Jerry Chi at Georgia Tech. Before I dive into this specific material, and these are some pioneering works that has been there for a long time. For example, Martin City's group at Max Planck Institute, and also Brett Nelson at ETH. Basically, all the works we're looking at here are pretty much developed based on the materials deformation. And the reason that it can deform relatively easily is because the material itself, it's very, very soft. It's very good for deforming structures, but in the meantime, it's bringing us a lot of challenges in terms of, because for functional composite, we wanted to interact with objects, not only to deform, right? So because of the soft nature of the material, in many cases, it cannot provide enough grabbing force for soft grippers or just enough driving force to interact with external objects. And then what we want to do is to develop a composite that can deform. It can be deformable, very soft. It can have this shape morphing capability. In the meantime, it would provide us with enough driving force to interact with other objects. And to introduce this new composite called magnetic shape memory polymer, basically this is a multi-physics material. It couples magnetic behavior, thermal behavior, and also shape morphing, which is a mechanical part. So what we did here is that we embed two types of magnetic particles. One is the hard magnetic particle called neodymium iron boron that is in charge of shape morphing, and another particle is just iron oxide. And what we're doing here is that we embed these two particles in shape memory polymer, which is a material that can change its rigidity under temperature change. So basically what we see over here, this is a mechanical characterization of the material, and also then a neat magnetic shape memory polymer and the shape memory polymer itself. So there is a very important temperature, which is a critical temperature here called the glass transition temperature. Basically, if we look at the storage modulus, which is just the Young's modulus of the composite, and at room temperature, it's really stiff. It basically behaves like a glass. It shows glassy behavior. And then if the Young's modulus is beyond gigapascal. And now if we increase the temperature of the material, and once it goes across the glass transition temperature, it will drop the rigidity significantly. And eventually, if we look at some temperature around 80 degrees C, you can see that the material would even drop below megapascal level. So it actually shifts 3 orders of magnitude in terms of the Young's modulus. And through this transition, we can actually tune the rigidity of the material, and then combined with the shape morphing capability, we can have a composite that can give us deformability. In the meantime, it can potentially give us enough force to interact with other objects by tuning the rigidity. So again, what we still want to do everything untetheredly, right? So we use magnetic field to control the shape morphing. And what we're doing here is that we also use a magnetic field to generate heat. So the concept is that we applied a coupled magnetic field. So the black curve that we see over here, this is for shape morphing. Basically, we're just applying an up-down magnetic field to trigger the beam bending of this strip over here. And then the red curve, that is actually a high frequency alternating magnetic field to trigger magnetic hysteresis loss for induction heating. So if we look at this video here, we can see that through the thermal camera, we can see the material gradually unlock and because of the temperature increase. And now it becomes really soft. It can very easily deform, have very large shape change. And then after that, we can cool it down so that it locks its deformed configuration. And at this state, we don't even need to apply other external magnetic field, and it can always lock into the deformed configuration. So based on this material, again, I mentioned that for soft materials, it's great. It can be deformable. It's very easily to generate different morphing shapes. But in terms of functionality, if we look at this soft gripper, right? So this is made of magnetic shape memory polymer. When we heat it up, it becomes really soft, right? It's just like whatever other soft materials. And now we are trying to grab this very heavy ball. It doesn't do it because it's too soft. It does not provide enough driving force. But now we can just easily tune the rigidity through the temperature manipulation. And once it's at room temperature, it becomes really stiff. Now we can successfully lift this object. And then by increase the temperature again by induction heating, it can cut loose this object. So basically we develop a robust soft gripper that can actually tune its rigidity to interact with the object. And then by kind of tuning the particle concentration in the soft composite, we could actually develop very, very small grippers that can grab something that is over 1,000 of its own weight. And for the biomedical application, potential biomedical application of this material is that we are always looking at whether we can use these different technologies that we develop for minimally invasive or even non-invasive operations. One example is called the TAVR procedure, which is the transcatheter aortic valve replacement. So basically what the procedure does is that the surgeon will need to insert a guide wire with a catheter all the way from the femoral vein. It make a cut from the femoral vein and then insert everything from there, and they goes all the way to the heart. And when it reaches the heart, it will need to make this 180-degree turn. And then the conventional guide wire is actually made of stainless steel. So there's a reason for it to be really stiff, right? We know that stainless steels are very, very stiff material. It has a Young's modulus over 200 gigapascal. So the reason that the guide wire need to be really stiff is that it's a very, very long journey to reach the heart. And through this journey, well, there are high potential that if we have a very soft guide wire, it's going to cause buckling and it will never reach the heart. So that's the reason that we need the guide wire to be very stiff. But the problem is that once we reach the heart, it will need to make this 180-degree turn. And the one challenge is that it's not very easy to center the guide wire. And because following this procedure, the surgeon will need to expand the stent to replace the old aortic valve. And without centering the guide wire, it will cause a lot of trouble. So with the new magnetic membrane polymer, we can actually easily tune the rigidity of it, and still we can fully have a fully functional guide wire in the very beginning where we are at the body temperature. It's really stiff and it can prevent any type of buckling when it goes to the heart. And once it reaches the need to make this 180-degree turn and need to be centered, we can easily apply external magnetic field to soften it, basically increase the temperature, change the rigidity, and then we can use the actuation magnetic field to easily change the orientation of the guide wire to center it. So another thoughts that we also combine 3D printing and also multi-material printing technology to directly print this composite. And we could easily program the magnetization distribution by just by changing the printing direction. So what we're doing here is that we apply a magnetic field during printing, and this magnetic field is will align the polarity of the magnetic particles in the polymer resin. And then through changing the printing direction, we're actually changing the magnetization direction of each filament. And through this way, we can very easily program the distribution of magnetization to give us the desired deformation. So what we're doing here is that we're printing nanomaterials, and nanomaterial is also like truss structure that are very commonly used for biomedical stents. And then from this way, we could easily print a retrievable stent, meaning that it's active, right? So once it's deployed, we could also deform it to tune its orientation, to tune its deformation, so that it could give us a desired morphed shape to match the blood vessels geometry. So now let me switch gear to another topic, the second topic of today's talk, which is the magnetic origami robot. So this paper is about to publish in Nature Communications, is currently in production. So the motivation again is still about minimally invasive and non-invasive operations, right? So if we think about the current state-of-the-art disease diagnosis and treatment technologies, they're all based on catheters, guide wires, and tubes and probes. And then we talk about the aortic valve replacement surgery previously, and now if well, very simply think about the upper endoscopy, we actually need very agile motion at the tip. So, but this motion is completely limited by the limited degree of freedom from the far end. So the idea is that if we could think about using magnetic actuation and develop a device that could give us very agile motion at the region that we want it to be, we wanted to navigate through very complicated terrains. And if we could have that agile motion and combine with some functional operations, then that would be great. So we are thinking about this problem, and then we are actually borrowing the very effective rotational motion from our daily life, right? If we think about the rotational motion for on-ground, basically a sphere can give us a very effective on-ground rolling to omnidirections. And another thought, if we think about in water applications, rotation is also the most effective way to provide propulsion just by rotating this propeller blade. But if we're looking for, so for biomedical applications, most of the case we're looking at a very hybrid environment, right? So the device would be what we desire, we want to have this device to have the capability in both on ground and also in water. So basically, if we could think about something that can combine the capability of having effective on-ground motion and in water motion, then technically we could develop an amphibious robot for this highly integrated hybrid motion. So this is what we did. Basically, we are relying on a origami structure called Crestling. And so the figure on the right, this is how we are actually assembling this small structure from 2D to 3D. So what we did is that we just need to cut the Crestling pattern from the 2D and then assemble it, fold it into a 3D structure. So I actually have a larger version of this structure. So basically it's a foldable, and I will show where this pattern comes from. So it's a foldable device like this. When we apply twist or compression, it's gonna fold. So the idea of using this structure is that it still gives us, we designed the structure to have a global aspect ratio closer to 1, so that it could still give us a capability of rolling, flipping, and most importantly, and very interestingly, you can see this tilted panel on the lateral side. That actually serves as a propeller blade. So if we spin it really fast in water, it's gonna, ideally, we wanted to see a propelling behavior. So this pattern is actually comes from mechanics instability. If we have a hollow cylinder and we grab the two ends and apply twisting and compression in the same time, so that is the natural pattern that we got from this instability. And again, this comes from this naturally evolved instability pattern, and that we're using it for its foldability, right? So it's foldable, and later on you will see that how we're using this foldability for the biomedical device as a pumping mechanism for targeted drug delivery. And then back to our own design. So to drive the motion of it, we just attach a magnetic soft composite on the lateral side, and now through a rotational magnetic field, the very nice and interesting thing is that no matter what orientation the robot initially has, we just apply the rotational magnetic field to the moving direction that we want it to go, and they will always decide which motion mode to use, either rolling or flipping, depends on its own interaction with the terrain feature, right? So previously that one was preferring to use a flipping mode, but when we have a very smooth, like inclined surface, we would prefer to have a rolling mode to go over different terrain features. And we're not changing any of the external magnetic field control. What we're doing is just by applying a rotational magnetic field towards the desired moving direction. So what we're really interested is the swimming capability. So basically what it does is that we're just spinning it really fast in a water tank. And this video that you see that is that we add rheoscopic particles in the fluid so that we can see the turbulent flow it generated when we spin it. So basically it's still based on the propeller-like structure that we have for the origami. And also if we change the spinning frequency, here we can see is that from 20 Hertz to 30 Hertz, and it's just under very small magnetic field, it's like 10 millitesla. And we can tune the swimming speed of the robot. And this is a slow motion showing the spinning motion of it. All right, and we're also collaborating with my colleague Gianluca Iacarino. Basically, he does CFD simulation to study the propelling behavior. So what is very interesting is that we actually had want to decouple the swimming mechanism. I mentioned the propeller blade. Well, intuitively, it's just like a propeller blade, right? It generates propulsion. It's very easy to understand. But for our robotic design, we also have this hole in the front. It's a thin shell structure, right? So we want to have a hole in the front so that we can still utilize the internal space for other functions. And then we actually also have this lateral slits. Due to the assembling process from the 2D to 3D, we naturally generate this slits. So what is very interesting is that we see the robot actually swims much faster with the hole and the slit. So this is a swimming speed comparison of these two designs. One is with the hole and the slit, one is without the hole and slit. And so one with the hole and slit, it will swim much faster. So based on the CFD simulation, we can look at a streamline when we spin a robot. But what is very interesting that we found is that for the design with the hole in the slit, it actually sucks water in from the front and then spins it out from the slit. So basically what it does is that it generates a very, very low or even negative pressure inside of the origami robot. And that decreases the resistance of the during swimming, and then leads to a faster swimming. And later on, we're thinking, okay, now we can generate this negative pressure. Now what we can do to take advantage of this negative pressure, not only just to give us some faster swimming. So this negative pressure can actually be used for a suction mechanism. So basically we're still spinning it, and naturally it will have this swimming motion to the target. And once it reaches the target, it could create this suction force to just suck in an object. So again, now we are using this origami, which is a thin shell structure, and we can take advantage of its internal cavity to store any objects that we want to take. And up to now, I only mentioned the rigid body motion, right? So basically it's based on the rigid body motion for in water propulsion, for suction to capturing objects, for cargo transportation, and also for on-ground motion. It's just going to be based on its geometric feature, how it interacts with a terrain feature to have interesting locomotion. And to steer the orientation of the robot, we would just need to change the rotational plane of the magnetic field, and that could give us a completely fully controlled 2D swimming path or a 3D swimming path. So this video further shows that we develop environments that could better show its amphibious locomotion, and you can see that it could rely on rolling and flipping to go over different obstacles, and they can jump into the water, and then it's going to be our small grabbing behavior, and then carry this object to swim to the target position, and then spin again to release it. And eventually, the robot can just swim back to where it came from. And for this part, you can also see that it's capable of swimming at the interface of the water and the air. So in all of these I'm showing here is still based on the rigid body motion, right? There's no deformability, there's no foldability at all. And next, I'm going to show you how we're going to integrate the foldability into a pumping mechanism for targeted drug delivery, and really makes it this small robot, this millimeter robot, into a multifunctional device. So basically the idea is that we still remember how the origami folds. So we just need to apply twisting, and that twisting is coupled with compression. So in this case, we attach two magnetic plates on the lateral side, and when we apply a magnetic field along the net magnetization direction, it's gonna generate torque to twist the two magnetic plates, and that torque is gonna compress the whole thing, and that will be converted to a pumping mechanism for targeted drug delivery. So this video further shows how we could use this small robot to pump at different locations and with different doses. For example, this first position, it pumped 3 times. It's a lower dose, and then it moved to the second position and pump more times. And we could control the dose by just controlling the number of pumps it has. All right, so lastly, I just want to mention that we still have other origami related work. If you're interested to looking more about the assembly of this origami robot controlled by external magnetic field, feel free to visit several of these papers. And then I would like to acknowledge my students, my team at Stanford, and my collaborators. Gianluca Iacarino did all the CFD work, and we're also collaborating with people from the School of Medicine for some animal experiments, and Joe DeSimone on 3D printing of very small scale robots. We're now doing 2 millimeter and 3 millimeter ones for biomedical devices actually in blood vessel. And lastly, my collaborator Jerry Chia, Georgia Tech, for the shape memory polymer work. Thank you so much. for attention.
Thank you very much for this great talk. It's fascinating to see these robots capturing things and so on. Never know that this is actually possible. So I have a lot of questions, but I might ask them in our coffee break because we're a little bit behind our schedule. So do we have other questions maybe online? You have now the option to ask.
Hi, Professor Zhao. Great talk, really fascinating stuff. I was wondering in terms of the applications for like for medicine, what you guys are thinking about in terms of like biocompatibility, because if you're deploying this in the body, like what are some things you have to kind of consider there in terms of biocompatibility with the body? Yeah.
So what we're doing now is that so the magnetic particle, especially the iron oxide particle, well, previously it was used for a procedure called hyperthermia. Basically, that particle is actually biocompatible. What we're doing now is that we're using combining 3D printing technology to print biocompatible and biodegradable materials that could, in the meantime, embed biocompatible particles to achieve all the same functions right now. That's a good question.
With regard to your amphibious origami spinner, I was a little confused on how it generates negative pressure underwater.
Yeah, so basically that is based on the suction mechanism that I briefly showed because limited time. So when it spins, we have a hole in the front and a slit on the lateral side. When it spins, it creates a negative pressure by sucking in the water from the front hole, and the water got spin out from the cuts, from the slits. That constantly generates a very, very low pressure inside of the robot and also in front of the robot.
Okay, I see. Thank you.
Sure.
Hi, that was a really awesome talk. I just wanted to ask if you're concerned at all about the turbulent flows that are generated in your drug delivery system and the effects that might have in the body.
Yeah, that's a great question. So we are working with several doctors right now for different applications. One is to remove blood clot in basically in blood vessels. Another is to capture kidney stones. So for different applications, we're actually looking at well, the turbulent flow would have different impacts, right? For kidney stone, it's not a big deal, but for blood vessel, so basically this procedure would be, well, the current state of our procedure would be something that they have a guide wire and catheter go into the blood vessel, especially for the treatment of removing blood plaque development on artery wall, and also for removing very big blood clots. So they are going to expand a balloon actually to stop or even reduce the blood flow so that you can do your operation well with a very low flow rate environment. So this is also something that we want to test working together with the doctors to see whether our technology could be compatible with the existing technologies in the biomedical operation. But that's a very good question.
Well, just one more quick question. So to generate these magnetic fields, is this like a large device, like an MRI machine that you would put the person inside of? Okay, cool.
Yes.
Thank you.
Great research. Thanks a lot for your presentation. I was wondering how you generate the magnetic fields that actually produce, for example, this little movie of your robot moving about and picking something up. Are these sort of teleoperated, or is there some programmatic way of achieving those?
Yeah, so basically what we're using to generate the magnetic field is a 3-axis Helmholtz coil that generates homogeneous 3-dimensional magnetic fields. And we have so all the motions can be programmed based on if we have a desired path, then we just automatically program it, and then the robot will follow exactly where we want it to be. And for other functionalities, such as we have a random object we need to pick, then it's just we have a joystick, and that motion is directly programmed to have like X and Y and Z axis motion and all the rotational degree of freedoms. And we just use a joystick to control the motion of the robot.
I would like to now hand over to Professor Barbara Mazzolai. I hope she's yeah, I can see.
Hi there, I'm here.
Yeah, we can hear you.
Okay, thank you. Thank you for inviting me. It's my great pleasure to, in some way, contribute to this very interesting discussion on how we can use a soft material for increasing the abilities in soft robotics. And this is also our topics, and this is in particular important. They say that this is also the long-term perspective. So in soft robotics, we want to use our robots also to address and to operate in real environments. And so we know that it's a very demanding, very challenging from many aspects in terms of energy, but in terms of control, the material, and so on. And but so the question is, in our case, can living beings offer new insights? And of course, the reply for us is yes. But on the other hand, we have to consider that natural organisms are in fact imperfect systems. So we are imperfect systems. And so what is relevant in designing the new generation robots is in particular the adaptation capability of living systems. So, and among many features, what is relevant for us is are the flexibility and plasticity of living beings and the way in which they can adapt to very unstructured conditions. So this is what we are trying to imitate in our system. In fact, our approach is deeply based on bioinspiration. So we take inspiration from different system, living beings, for developing robots, software robots for industrial domains, in particular for manipulation grasping, but also for exploration, monitoring, and in particular for environmental protection. These are the scenarios that we have in mind. And also, since these robots are based on the bioinspiration from the design phase, in some cases, our goal is also to use these robots for validate an hypothesis on the biological systems that we take as a model. So this is the double goal of our research. And as a model, we have, in particular, invertebrates, soft animals, octopus, earthworms for soil exploration, but also plants. So we are study plants, in particular, their movements and exploration capability to develop new robots. And today, I would like to focus on plants as a model for giving some ideas of what we are doing, especially in developing these adaptable software robots. And I would like to talk about our research in growing and climbing robots, in soft body robots, and variable stiffness robots. But the first point, we started more than 10 years ago to propose plans, in particular plant roots, for developing autonomous robots for soil exploration, what we call a plantoid actually. And our model, among many living beings that live in soil, was a root, the plant roots, because they are the most adaptable living beings, because they overcome the high pressure and friction in soil by moving by growing. So they add new cells by cell division in the tip of the root. They absorb the water by osmosis, and then they push only the tip in soil. And this is the way in which they are so, effective in penetrating soil. And in the tip, they also have a sensing properties, so they perceive gravity, humidity, chemicals, they can avoid obstacle. And there are behaviors associated to these sensing properties, so they can grow following or escaping from environmental stimuli. And we are also studying the communication capability among the same root apparatus of other plants. And so the way in which we translate the growing capability, so we spend at least a couple of years, but more, to understand this is the secret in plants to grow. And this is one of the robots that we developed some years ago that is based on a 3D printed machine inside the head of the robot. So there is a motor that pulls a filament that is a thermoplastic material from a spool. And then there are gears, as you can see in the cartoon, the simulation. So gears that allow the perfect deposition, the new layer in contact with the tip. But inside the head, there is a resistor. So we increase the temperature for a few seconds. The material becomes sticky and can adhere to the previous layer. So, and layer by layer, the robot is able to create some body. So this is the way in which we imitate the growing capability. And the direction growing is given by the sensor integrated in the tip. So we also have this tropism, this behavior associated to the growing. So the robot autonomously can decide the direction of growing. So what we can do is just to show you some of the application, some project funded by the Tuscany region to detect the temperature and the humidity in the first layer of soil. So again, as I mentioned, the robot autonomously can look for these parameters into the soil and then provide information to the humans and human operators. But it's not a growing, it's not adjusting soil. This is the way in which plants show high plasticity, as I mentioned. So they change continuously the morphology, adapting the morphology to the external feedback. This is quite a unique feature among the living beings. And we are also studying growing and climbing plants. So they are quite peculiar because they use most of the energy to go faster towards light with respect to the other plants. And of course, they have to anchor the body to avoid to collapse. And so what we are implementing is a completely different behavior because our robot in this case have to move against gravity. So what we are implementing is gravitropism that is a negative. And so also in our case, the robot is able to train around the support to sustain the weight, but also to follow different stimuli like light, for example. This is a stimulus also to guide the movement of the robot, for example, to avoid crossing, to overcome obstacle, but also to adapt to very unstructured environment. In the left, on the bottom video, you can see how we exploit the melting properties of the material to attain a robot that can, without any control, adapt the shape to the external environment. So we exploit when the material is melting, in fact, is quite adaptable, and so we can quite soft. We can use without any control to move into very unstructured environment. But very interesting, climbing plants can provide new ideas also for developing other devices. So this is also the case of this climbing plant that is named Galloapari, that is quite peculiar because it's a parasitic plant that use the hooks that cover the surface of the leaves, in particular the ventral part of the leaves, to attach to the leaves of the hosting plant. And this is is a sort of racket mechanism, so the plant can attach to the hosting plant to be better exposed to light. You can see the Gallium aparin and the Salvia officinale. You can see also the different velocity in the movement of the climbing plant. And what we did, we started from the anatomy of these hooks, and we developed artificial hooks by imitating the shape, the morphology, but also the mechanical properties of the material. And we develop artificial hooks by using a photolithography machine, the nanoscribing machine. So what we generate is an array of these hooks with an oriented angle, and we can of course play with these hooks. This is the case of this mini car that will be in some way we integrated these hooks on the wheels of this car in order to attain a climbing behavior. And so only when the hooks are attached to the wheels, the mini car is able to climb over a 45-degree inclined plane on different tissue, on different roughness of tissue. And so this is very effective to develop this climbing robot, but more than this, what we are doing is developing devices that can be very useful in precision agriculture and sustainable agriculture. So we can attach such devices to the natural leaves, and we can detect in situ and real-time temperature, humidity, light, different parameters that give information the stress of the plant. And also we are working on a biodegradable version, these hooks that can be attached to the leaves to release a substance directly on the vascular tissue of the plant. So this is the first prototype. So what we are in particular release are drugs in order to avoid the release of pollutants into the environment and moving, as I mentioned, to a sustainable agriculture. But also, we are investigating plans for developing soft body robots, and this is the case of this movement that we can observe in plants. The way in which plants release a seed are demanded to this structure that are completely without metabolism, so are dead structures that continue to move thanks to the arrangement of the material in the cell wall, the fact that some material absorb and dissolve water, and other material in the form of microfibrils, depending on the arrangement, they play the movement. So we can have a bending, coiling, flying seed, and so on. And so we start some years ago to implement such arrangement with Virginio Mattoli. So we use the pivot PSS, that is the sensitive part, the sensitive layer. So it can interact with the humidity, absorb and dissolve the humidity, and PDMS, that is the inert layer, so drives the movement. And since the pivot is also conductive, we can apply a current to the system by Joule effect. We release the water and we can control, in fact, the movement. What is very interesting from our perspective is that these hygromorphic actuators can in fact also play as a sensor, in this case as a humidity and temperature sensor, and can have a passive but also active movement, so we can control in fact the movement. And now very recently we start a new project, an European funded project, in which the goal is to develop an ecosystem of seed-like soft robots that can be used, in fact, to detect different targets, different parameters in the environment, like humidity, temperature, but also mercury, in particular elemental mercury, CO2. And so we developed these soft robots that are covered with fluorescent material that emit fluorescence when they interact with the target. And the fluorescence is read by LiDAR techniques on board the drones. So what we are doing, just to show you some of the preliminary results that we achieved, these are the models that we are investigating. So the pelargonium, the rhodium as a drilling seed, but also seeds that are able to fly, like the acer, so the samara seed, the tragopogon seed, that are based essentially on lignin and cellulose, that are the sensitive material. The cellulose interact with the humidity. And from an artificial side, these are the material that we are using right now. So PLA with the wood, PCL, cellulose, but also lignin and cellulose to have a short-term biodegradability. And these are the first results. So we started from the arrangement, the organization of the layer, the active and passive layer in the real seed, and we implement a similar structure in the artificial seed. So what we obtain is the movement is associated to the interaction with external humidity. And very important, like in the natural seed, by chance, so these robots move into the environment and then can entering, crack in soil without any control. The control is given by the external humidity. And in terms of flying seed, what we are doing is, again, starting from the parameters in natural seed, in terms of speed, in terms of rotational velocity, wing tip speed, the cone angle, that are fundamental to achieve then the geometry of this artificial seed. Then you can see the place in which we will put the active material to detect the temperature, humidity, CO2, and mercury. And then this is the scenario that we have in mind. So release these soft seed, artificial seed that are also biodegradable, since we cannot retrieve these soft robots because they are too small. And so we release into the environment and are biodegradable. And so after a while, they are degraded by the natural component and can read the parameter by using the LiDAR. So the idea is to use also in remote areas where the traditional techniques cannot reach, cannot work. And then the last point that I would like to mention is how we can generate a robot with a variable stiffness, also take inspiration from plants. So we know that plants don't have a muscle, but they can, in fact, increase the stiffness by play with the water inside the tissues. In particular, by osmosis, they can generate this flow of water inside the cells, as I mentioned. So the water moves from one side with a lower ionic concentration to one side with a higher ionic concentration. And this flow generates a turgor inside the cell. And so we developed several osmotic actuators, but I would like to show one of the last prototype that we have developed based on this concept. Again, we started from climbing plant. This is the tendril is one of the systems used by climbing plant to anchor to external support. And what we develop is a completely soft robot based on PET material, in which we put soft electrodes based on carbon fibers and an osmotic membrane. And we can apply a low voltage to the system to, in some way, absorb and dissolve ions and to have a consequent movement of water inside the soft arm. And this is the way in which we can increase, in fact, the stiffness. So what we obtained, in fact, is a software robot that can completely coil and uncoil around the support. We apply 1.3 volt, so it's quite as a source to generate these absorption and desorption ions, as I mentioned. And what we can obtain in around 25 minutes is the coiling and uncoiling of the system. So the system is completely reversible, and during the movement of water, as I mentioned, we can increase the stiffness. But there is also another way in which we can increase the stiffness in a tendril soft-like robot. This is a completely different approach. So in this case, we have two silicon layers. One layer, the first layer, is uniaxially stretched, and the other one is a relaxed layer of silicon. So what we can do is control change the angle of the structured silicon in order to, by design, obtain a specific, in fact, coiling around a support. What is very interesting, when, since inside the system there is a PCL core and an heating element, when the PCL is solid, the tendril is in the strain configuration. But when we apply, in fact, a current to the system, what we obtain is a melting process. So the PCL becomes liquid, and the pre-stretched silicon layer can release, in fact, the energy stored. And so what we have is a coiling mechanism. As I mentioned, we obtain this calling depending on the angle of the fiber inside the system. And when we stop eating, the PCL becomes again solid, and what we obtain is a sort of lignification, like in the natural tendril. So what we obtain is an increase of the stiffness. So in the natural tendril, this is obtained by a change in the material. But what we can achieve is, in fact, a difference, the stiffness of this soft at the end arm by play with the PCL core inside the structure. And so we can use it for anchoring and maintain, in this case, the anchoring to or the attachment of a robot or different devices. In this case, the process is not reversible like in the natural tendril. So to conclude, it's evident that we can play with the material, also adding some functionalities to the material, like sensing, actuation, also energy, form of a communication. It's very important in some way reduce also the energy consumption by play with the design. So like in it's very evident in plant that they play with the design in order to reduce the energy consumption, because they cannot move like animals. So they can in some way use the resources that they have. So they implement different strategies to reduce the energy and at the same time to interact with external conditions. So this is something that we want to implement in our robot as well. And also another features in the long-term perspective, we know that it's very complex. So these are a few examples. I see the robot, but they are quite simple in terms of geometry. It's much more complex if you increase the complexity of the robot. But what we would like to achieve is a sort of cycle life for our robot in which they can play, or they can act in the environment, they can grow, they can evolve, they use energy from the environment. But then at a certain point, they disappear because they are biodegradable or reusable. And this is, of course, the challenge that we would like to address in the next future. So I would like to thank my colleague that worked with me on this topic, a young researcher that comes from different disciplines, the funding agency, and all of you for your kind attention. Thank you very much.
Thank you very much for your great talk. I really like the fact that you keep in mind the biodegradability with your robots, because I think that is a big part, especially when we go to having robots in the field, deploying them everywhere in agriculture and so on. Yeah, so this is a great fact. I would directly like to give the possibility now to the audience to ask questions online or in person.
Good afternoon, Barbara. Thank you very much for your talk and sharing all these exciting projects and research results with us. My question is regarding your growing robot, and I understand that the forces that you can exert to the soil is probably limited to the material and the pressure that you apply to the soil, and then the curing time of that material. So I was wondering if you have experimented with different type of materials and with different mechanisms to shift the material in order to grow your robot into this media.
Thank you very much for this very important question. So this is exactly what we are trying to address. So we use a PLA, and now with PLA we plus wood to increase also the biodegradability that I mentioned before. But there are some constraints that we have to achieve. We have to take in consideration. So the first one is we need to create a structure. And so a continuous structure. So now PLA is quite effective in terms of achieving this layer by layer growing system. But as you mentioned, we have several limitations, especially because in roots, what is relevant is not only the growing that we can achieve in this way, but more than this is the elongation. So they absorb the water, as I mentioned, so they play as a sort of a hydraulic system. And with the PLA now, we don't have this functionality because it's an inert material. It cannot interact with the humidity like other material that I've shown. So now we are trying to find the material. So we have some preliminary experiment to create the structure, but also obtaining this elongation capability to achieve a more force, as a higher force, as you mentioned, because now the force that we can achieve is quite limited in comparison with what is needed to penetrate in a deep soil. So now we just penetrate 10 centimeter maximum with such a system, but we could do much better if we obtain the elongation. So this is our challenge, and we have some material in mind. We are also merging wood and cellulose because this is an active material that can absorb the water. And this is one of the challenges that we are facing, but you are right, this is exactly the next step for our growing system.
Yeah, thank you very much also from my side, again, for this great talk. I would like to now go on to not fall too much behind our time schedule with Ingrid Graz.
So I would like to thank you for having me today. So I should also say thank you for the previous speakers. It was quite cool to see all these materials. And I should say my background is more in stretchable electronics, and I'm a physicist. And so it's always cool to see if there is materials that actually can really do some amazing things. And today I would like to show you a little bit, basically a soft material physicist take on soft robotics that are inspired by plants. And yes, so we have heard a little bit about plants today, but I actually wanted to start with something that always amazes me and also my child. So the big question is, can plants move? And we heard today from Barbara before, the plants can move, and they cannot move like Groot in Guardians of the Galaxy, but they rather move like the little Groot that is dancing in his little pot. So they basically are able to move, although they seem to move quite slow. And just to summarize, I mean, we've heard little bits and pieces from previous speakers, and I wanted to give you like a little overview on typical plant movements. And basically, we distinguish between tropism and nastism. Tropism means that always the motion is oriented towards or away from a stimuli. And there can be different stimuli. It could be light, so we're talking about phototropism, or thigmotropism, which means if you touch the plant, it will move. Then there is chemotropism, which is due to chemical substances. So that means if there is plants basically talk to each other by putting different chemicals into the soil by the roots. And so other plants will maybe move away by just retracting the roots and just not expanding in that direction. There's hydrotropism, which means like it's directed to water. And one of the most common ones is a gravitropism, which means plants are moving towards the direction of the gravitation. So basically, if a plant in outer space, or if you put it on the ISS, it will basically move in all different directions because there's no real gravitation. Nastic movements are basically not oriented towards or away from the stimuli, but also they have no orientation, but they also are in reaction to touch, temperature, humidity, light irradiance, weight, chemicals, or nutrients. And one of the questions is, can plants really move fast? So we all know I have some plants on my, you cannot see, I have some plants on my windowsill, and when they grow, so basically this is quite a slow movement. But there have some biologists really looked into if plants can move fast. And so there is two examples that I just want to show you. There's two examples of fast moving plants. One is the mimosa. So basically what you can see is if you touch it, it basically folds up its leaves. And the other one is the Venus flytrap or Dionea, which basically you can see this bug is moving across this Venus flytrap, and it has these little hairs here. And when the bug is touching, it basically closes and can digest or eat the bug. And so both of these movements, where we're from the Mimosa and the Dionea, are basically thigmonastic movements. That means it's a nastic movement. It's not away or towards the stimuli, and it's a reaction to touching. So the question is, why can these plants move so fast? And there was some work done by biologists, but also mechanical engineers that looked into what are the mechanisms behind these fast movements of plants. And what they basically found is that there is two major movements or driving forces behind. So what you see up here is water-driven movements, swelling and growth, due to the cell pressure of the water into the cell, the sugar, like Barbara mentioned before. And down here, you can see the other big driving force is mechanical instabilities, so buckling and cracks. This is basically used for expelling seeds quite often. And what you can also see that there is a list of plants that these people researched, and you can see that the time scale and the tissue size play an important role. So below this blue line, there is no water-driven movements possible. And below this red line, there is basically no movements possible at all. And when you look, the Mimosa is in blue, is right on the border between water-driven and mechanical instabilities. And here you can see the Venus flytrap, which is a mechanical instability driven by buckling. And I would like to show you in the next few slides some little actuators or robots we built inspired by these two plants using water-driven swelling and growth and mechanical instability. Before I go into that, I just wanted to talk shortly about the water pressure inside the cells. So this is basically what's keeping the cells upright, and Barbara was already mentioning this can actually make huge difference. If you now look here down at the fern, Lepospargorium, here you can see it has a negative pressure, and this is really used to expel the seeds. So basically it's like a little catapult that's kind of like folding up by actually decreasing the pressure so much and then basically expelling the seeds. You can also see typical pressure of a car tire, blood pressure, or a muscle, and it can be the turgor or the pressure within the cells can actually be quite large in comparison. So it's a powerful tool, the osmotic pressure within these cell walls. Okay, so first I would like to start with the Mimosa, and the Mimosa uses the swelling and the shrinking for its thigmonastic movement. So what you see here basically is a photograph of the Mimosa, and here's the leaf, so here. And what it's using actually is called the pull-venous hinge. So here you can see a little schematic, and what you have is basically adjacent layers of cells, and these cell layers basically create this kind of antagonistic movement of swelling and shrinking. So when the upper layer is shrinking and the lower layer is expanded, so the water pressure is changed between those two, you have this motion upwards. And if you increase, or if the water pressure in the top layer is increased and in the lower layer is decreased, you basically have this downward movement. So you basically see that it's purely osmotic pressure within the cell layers, and you can also see it takes about 20 seconds to change the water pressure in the adjacent cell layers and basically do this movement. And we took this as an example to make a little phase change actuator, and today actually we saw already some materials that basically use this phase change or use this change at the very first talk, or the second talk and the first talk. And what we basically did is we used, I've heard already that people said people use a lot of silicone, and this is where I come from the background of stretchable electronics. So we use silicone rubber, and what we created was a little liquid reservoir within our bulk silicone material. We inserted a resistor and basically connected it up to a power supply. And on the top, we put a very thin membrane to seal this liquid in. And what happens if you basically heat it up, it's like what you do in a pressure cooker. So you see that this membrane expands, and you have a volume expansion. Since the liquid evaporates and the gas expands, you have a volume expansion about 120%. And we were using this to create a little actuator. What you can see here is these bubbles pushing against each other, and we're making this little hinge where we can actually really have a nice motion, a nice bending motion. What was interesting to us and what we did not expect, if you look here, so we apply a voltage of about 10 volts. We have this 100 ohm resistor. And what we obtain, we use different low boiling point liquids like acetone, ethanol, and water. And we can achieve forces up to 6 Newton, so which is for this little bubble, which is only like, I go back, is less than 1 centimeter in diameter, is quite a lot. The nice thing as well is when you see the expansion is quite fast. And what was surprising to us, when you assume you now need to cool down the liquid to go back from the gas phase, you can see we assume that would be a very slow process. But actually the membrane, the elastomer membrane at the top is kind of pushing back, and it has condensation. So what we also see that we have a quite fast shrinking of our little bubble. And basically what we can create is a very, very simple antagonistic swelling and shrinking with our phase transition actuator. So we actually made hinges to like this little gripper where it actually can lift devices. We also incorporated stretchable electrodes on top to actually monitor the bending action in change of resistance. And it's not very pretty, but it was a first attempt. And I think also it shows a little bit what are the challenges. So we made this little robot that's basically powered with a conventional battery that can basically lift and move its legs. What I should say, it was quite incapable of really walking because the body was too heavy. But basically what you can see, so we have different motions forward and also downwards. And I think it's a pure matter of design. Also, I should say this elastomeric materials are quite heavy, and this is a challenge to do this. One colleague of us, Aslan Miljev, took this further. So what he did, basically, he did not use this reservoir incorporated in an elastomeric bulk material. He basically just created ethanol drops and mixed them into this silicone rubber. And what you basically then have, you have this elastomer matrix, you have the ethanol liquid, and you also have a little bit of ethanol vapor and air. And by really basically pushing a wire through this kind of material composite and heating it up, what you have is that this ethanol liquid expands, basically evaporates. And what you can do by pushing a wire through, you can really create this actuating material. So basically it's a composite material. And what you can see also here is the material. It's just basically a foam or a composite between elastomer and ethanol. And you push a wire through, and then basically you also have this actuation and bending motion. I will basically, here the big challenge is we have these soft materials, but we also, like in the first talk, we have a material that's not that's gas permeable. So basically we are losing the active liquid or the ethanol during actuation. So this is a challenge for this device. Okay, the second actuator I would like to show you is something that's very close to my physics heart, because it's combining mechanical instability with what I showed you now. So the Venus flytraps use what's called the snap-through instability. So basically, if you look, or if biologists look at this Venus flytrap, what you see is this concave shape. So here you have layers, or basically you have a lot of tension when it's kind of open up. And when now a little animal or bug touches these hairs, I don't know if you can see them, there's very tiny hairs. It basically, these hairs are part of this, how do you say, yeah, they are under tension. And if they are touched, the whole concave shape basically transitions, snaps into a convex shape. And this is within 100 milliseconds, and it traps the bug. To basically recover from the convex to the concave shape, the water swelling and shrinking or Tugur is used. So basically to reopen the trap or the Venus flytrap, there is swelling and shrinking of the adjacent cell layers. And so basically we looked into that concept, and what we basically also have been researching for quite a while is balloon shapes. And what you see here is the pressure volume curve of a typical balloon, like one I have here. And so basically what you know all, if you inflate the balloon, you basically increase the pressure if you have the empty balloon, and you need a lot of pressure to have very small change in volume. As you go at a certain point, you start basically, it gets easier and easier to inflate the balloon. And then if the balloon is already like very much expanded, it becomes harder and harder, and at the end, basically the rubber will rupture. What you basically end up with this balloon is this N-shaped curve. If you're interested in balloons, I can really recommend this book by Müller and Strelov. They are doing a lot of balloon physics. But what was interesting to us in this curve, if you look here as a physicist, you have here at one point of at one pressure, you have two possible states of volume. So you have a small volume that's possible, and you do have a large volume that's possible at the same pressure. So we were wondering, can we possibly go from here, from this point, over to this point? So basically expand the volume with the snap-through instability. And what you would like to do is basically to do this snap over here. But that would be only possible if you were able to really keep the pressure constant. And I would show you our setup in a second. We were not able to control the pressure that well. So what we basically ended up doing is we got a reservoir. So we got an additional reservoir to our balloon. And then you basically don't have this straight jump over here if the pressure is constant, but you basically follow the gas hub above. And so basically you're jumping not straight, but you jump slightly down here. So when you slightly increase the pressure here with your rubber balloon in your reservoir, you jump over to this point. And when you then decrease the pressure, you're going back here and you have a snapback to this point. And we built a very simple demonstrator, and I should say it's really a simple demonstrator. It basically consists of a thin aluminium casing. It's a Red Bull can, and we basically use latex as the elastomer. We have a control for the pressure and a pressure sensor, and we slightly wanted to increase the pressure, and we have previously used this phase transition from liquid to gas phase. In this case, we basically use the same materials, where we use a little bit of a low boiling point liquid in our reservoir, and by slightly heating this liquid, we increase the pressure by a tiny bit to go from this point here up to here, and then we expect to jump over here and expand the volume. And what you can see here is the experiment. So this is the setup. We basically have here our aluminum can, and we touch it with the hand, and within 4 milliseconds, we are able to really trigger this instability. So basically what we do, the warmth of the hand is sufficient to trigger this tremor and this instability. So it's a change by 10 degrees in temperature. And I can show you a movie. So here you see the little balloon, and there you can see this big expansion of the volume, just triggered by a change of 10 degrees in temperature, by just touching and just evaporating a few more molecules to increase the pressure. And then you can see also going backwards. This actually takes much longer than previously with our phase transition actuator. So now we'll have a snapback. And I can play it once more. So basically you have the inflated membrane, you inflate a little bit more, and then you have a big change in the volume. So basically when we saw this, I know this is not a robot that will move and basically move things, but when we saw this, we immediately thought about protection equipment. So if you were, so I have a project where we're actually researching damping and impact protection. So the question is, can we not use this, because this is 4 milliseconds. This is as fast as you need airbag to inflate in your car to protect you, or to, if you fall, to actually create protective measures. And this would be as fast to really achieve this. I can also show you, we played a little bit around with this, and we wanted to see if we were able to, to use this. So basically when we built this little Lego gripper, where you basically have this little bubble expanding and going back, so you can actually grab something and build a grabber by combining it. Yes, and with this, I guess I was a little bit fast, but I would like to show you plants are actually stimuli responsive materials, and they can offer a lot of inspiration for fast actuation. We can actually compete with plants in terms of speed and size. And I showed you now this kind of gas transition, but what we also are exploring at the moment, what you see here is a liquid synapse through instability. So basically you fill this bubble with a little bit of liquid, and at some point you also have this instability of the balloon that's filled with liquid. That's actually quite fast and recovers quite fast. And it's basically the same system, but it's using a liquid. Overall, when we look at this mechanical instabilities and this phase transition, where we basically use vapor or low boiling point liquids to do some gas filled actuators, the need we have, and I think it was quite clear from the previous talk, is to have improved materials. So what we are using is off-the-shelf materials. And what you see here is silicone, rubber, and latex. And ideally, we would like to have new materials, and we're just trying to push colleagues in chemistry and material science to develop better materials that have improved gas tightness, that also we would be looking for materials with improved instabilities, so which have instabilities similar to those of natural rubber, and it's not that easy to accomplish with silicone rubbers. Also, when we want to do this type of actuators, there would be really a need for good crossability to create membranes that can be very, very thin, so below 10 nanometers, 10 micrometers of thickness. We have heard previously built-in stiffness gradient would be amazing, and also biodegradability, because in this case, if you use, for example, as a driving liquid, if you use water, you would have a completely biomimetical system where you have biodegradable material, and water is basically nothing harmful in it. And I hope to see that in the future. And with that, I would like to thank these students basically did the experiments for this talk I was giving today. I have other students working on these damping properties. I would also like to acknowledge my funding agency, and I hope we keep on moving in this direction with the soft actuators. And I'd like to thank you for your attention. Thank you.
Yeah, thank you very much for this very interesting talk. I didn't know that plants are that strong. Yeah, it was great that this was somehow a call for materials. So to all the material scientists that we have, please, we need, for in this example, unstable materials. So this was also new for me that this is sometimes asked for. I'm now happy to give to the audience. We have one question here already from the in-person audience.
Yeah, thank you very much. Another very inspiring talk, in fact, and thanks very much for sharing that with us today. I have, in fact, two questions, and I think that was regarding your little bubble that you actuated using temperature control. I think it was ethanol inside there. So the first question is, you used the antagonistic behavior to revert the actuation. Can you comment on if this antagonistic behavior of the bubble would not be there, how long it would take to revert the actuation? And the second question is, could you potentially look into using temperature control in combination with the tension of the bubble to increase stiffness?
Okay, so maybe I was not, so for this motion, so what you see here, this is basically really the bubble alone. There is no other bubble pushing against it. So the motion is the pushing, but this is basically just the force by the simple bubble. It's just really the membrane that helps so much. And we were surprised by that because we did not expect, we actually expected a very low cooling behavior and having a very slow actuation. So that was a surprise to us. And sorry, can you repeat your second question?
My second question was regarding, so if you use now temperature control, so you apply a voltage, but at the same time you can kind of use the tension of the membrane to add stiffness to your actuator or change stiffness.
Yeah, so we are actually, I mean, took me 5 years to convince the chemical synthesis people at our department of polymers. So we're actually at the moment trying to combine and to develop a material, and I can't yet show it, where we actually have temperature or energy input to soften the material, but it will still be have integrity. So it will still be one piece of material, but it will locally soften. So we're actually looking into that. And that was actually a topic for the damping behavior, because we wanted to adjust stiffness. If you have an impact, you want locally soften the material quite fast, but then actually restore the integrity of the material.
Yeah, thank you very much for this talk again.